Hi, in this video, we're going to be talking about what is a function and what is its domain. On the screen right now is what the formal mathematical definition of a function is. Really, what a function is you put one thing in and you get exactly one thing out. It has a domain. It's usually x. It can be other letters as well, but usually the x values is your domain, and your range is your output values. It's usually a y, but it could be other things. We also use this fun notation, f of x, to represent that, hey, this thing's output is following the rules of a function. A good way you can make sure to remember these is that they're all alphabetical. I comes before O in the alphabet, D comes before R in the alphabet, X comes before Y in the alphabet. Everything about functions is alphabetical. Right here, I've got an example and a non-example of a function. Here, we're saying triangle goes to lightning bolt, star goes to cloud, plus also goes to cloud, but that's okay because each one of these shapes outputs exactly one shape back. We don't want something like this where triangle has no output. That would be like a broken function or a broken vending machine where you put in $1 and you don't get anything back. We should get exactly one thing back for every input. This function overall is doubly in trouble because also we have problems with the plus. The plus has two outputs. It's outputting both a cloud and a moon. So whenever we have a function, we should put exactly one thing in, get exactly one thing out. Triangle and plus in this non-example are not following that rule. Here we have an example that's more mathematical, where we actually have some coordinate points. In order to help me determine whether or not these are functions, I made a t-table for the points. And we can see here with all of these inputs, they have similar outputs, but each one is only outputting 2. 3 is only outputting 2. We don't like what's happening over here, where 1, the first time we put it in, we get out a 2. The second time we put it in, we get out a 3. So that makes it not a function. We can output the same thing multiple times. That's okay. But when we put something in and we get different things out, that does not make it a function. In these examples, we are looking at equations. This first one is a mixture of different functions put together. I can see parts of our happy functions there. There's an absolute value function overall, which is a function, so that's okay. And then there's also a quadratic inside of there that is also a function, so that is a function overall. Over here, it's tough to tell if that thing is a function or not because x and y are kind of all mixed together. It's easier to tell when that y is all by itself. So I want to solve for y here to determine if this is a function. It's not a function. We're going to see why. I'm going to move that x plus 3 to the other side by subtracting that x plus 3 squared over here. And then in order to get rid of the squared on the y minus 2, I'm going to square root both sides. Because I did square root as a solving step, I need to put this plus or minus there. So the last thing to do to get y by itself is to add that 2 to the other side. Now I can tell that this thing is definitely not a function because every time I put in an x value, I could actually even tell it here, I'm getting multiple y values out. Every x value has 2 y values, so this thing is definitely not a function because each input has 2 outputs, and we want to make sure that each input has exactly one output. Graphs are the easiest way to tell if we have a function or not using the vertical line test. The vertical line test has us pass a vertical line across the function and see if it's ever touching twice. We can see in the non-example that, hey, right there, that thing is touching the curve multiple times. It's touching it twice. And it even happens more than once. There are lots of times where that thing fails the vertical line test, so that is definitely not a function. It has that same plus or minus issue that we saw before. Over here, this one, it's almost a function, except for right here. Right there, we fail the vertical line test. We're okay over here, we're okay over here, but right at that point, we've got 2 dots stacked above each other. So that thing is definitely not a function. It fails the vertical line test. If we look at the other one, we might be concerned because we pass the vertical line test here, we pass it over here, but you might be concerned about this area right here, because right here, we've got that same stacked dots that we had over here where we failed the vertical line test. But over here on this one, we've got a filled in circle and an open circle. And that open circle means we approach that point, but we never quite reach it. So we actually pass the vertical line test at that point. The same thing happens right here, where there are three dots stacked on top of each other, but two of them are open, meaning there's not actually anything there. The line is approaching that point, but not quite reaching it. The only point that we have at x equals -2 is this point down here, so we do pass the vertical line test. Now, the next thing I want to talk about is the domain of these functions, but I think it will be better if we talk about what to see based on equations first. So when looking at an equation, you're looking for these three things. And if you don't have any of these three things, then the domain is going to be all real numbers. So you're looking for x's in the denominator. The denominators can't be 0 because we can't divide by 0. If you have an x inside of a square root, then we have problems because we can't square root negative numbers. We get imaginaries, but on the y-axis, there's no spot for imaginary, so I don't know where to put that output. With logarithms, they can't take negative or 0, so it's kind of like double trouble from square root and denominators. But if we don't have any of those, then the domain is all real numbers. So we've got a couple examples here. If we are looking for that x in the denominator, what we do is we set that denominator equal to 0. Note that I don't care what's going on with that 3x minus 7. I'm only going to care about that denominator. I solve for x, and after solving for x, I say, okay, x cannot be that -3 because that -3 is going to make this denominator equal to 0, and that's not what I want. I want everything else except for -3. The easiest way to talk about that domain then is to make a quick number line with -3 on it. And then say, okay, well, I want everything around that. So I want an open parentheses here, parentheses there. So I've got everything that's less than -3 and everything that's bigger than -3. Then it's easy to write that interval notation by reading it from left to right. It'll be -infinity to -3, giving -3 a parentheses. We have a gap right at -3, and then -3 to infinity again. In this next example, we want to do that same process. I don't care about what's going on in that numerator. All I care about is what's going on in the denominator. I need to make sure that the denominator does not equal 0. So after doing a little solving, I square root both sides. By square rooting both sides, I need to add a plus or minus in front of the square root of 16, which is 4. And so now I've got two things that I want to avoid. So once again, to make it easy, I want everything but that 4 and -4. So I just plop them on a number line. And I want to make sure that I get everything that's less than -4, between -4 and 4, and greater than 4. So I want all this stuff. I want between, and I want everybody bigger. Because then once I make that number line and then make that quick graph, then it's just really easy to read that interval from left to right. I'm going to start down here at -infinity to -4. There's a gap right here at -4. -4 to 4. There's another gap right here at 4. And then we're going to go from 4 to infinity. If we are looking for restrictions inside of square roots, again, I don't care about anything that's happening outside of the square root. All I care about is what's in the square root, and that can't be a negative number. So I need to take whatever is inside the square root and set that greater than or equal to 0. It's always going to be greater than or equal to 0 for square roots because we never want to put negative numbers in there for it to be a function. We can do it to get an imaginary number, but again, I don't have anywhere on the y-axis to graph an imaginary number. So I want to avoid those for this function because otherwise I won't have an output. So I do a quick solve. X needs to be greater than or equal to -2. To make writing that domain easy, I really quickly take 2 seconds to make this number line. So -2, I want everybody bigger than -2. Since I have an equal to, I want to put a bracket at -2. And then I can just read this interval from left to right of -2 to infinity. In this example, I don't care about anything that's happening outside of the square root. So I don't care about this. I don't care about the 3. I don't even care about the square root. All I care about is what's inside of that square root. Inside of that square root needs to make sure that it does not create a negative number. So I set inside of that square root greater than or equal to 0. It's always going to be greater than or equal to 0 for a square root check for domain. So then I do a quick solve. I subtract 10 from both sides. I divide both sides by -2, keeping in mind that if I divide both sides by a negative, that flips my inequality. So that's why I have x is less than or equal to 5. And then just real fast, I draw a number line because it just makes it easy. Draw 5. I want less than 5, so I'm going to go in that direction. I put a bracket on the 5 because I've got an equal to, and then I can just read this interval from left to right. Now, following the arrow, reading the interval from left to right, I get -infinity to 5 for the domain of this function. I did not care about stuff on the outside. All I cared about is setting that inside greater than or equal to 0. For logarithms, we need to take whatever's inside of that logarithm and set it greater than 0, because logarithms, they can't take negative numbers and they can't take 0. They're very, very picky things. So they always are going to be greater than 0. I don't care about like an e to the x. That is not a logarithm. The only logarithm I've got in this example is that ln. So I just grab what's inside of that logarithm, that x plus 8, and I set it greater than 0. Then I do a quick solve. So x needs to be greater than -8. And then in order to state my domain, I just make a quick number line because that makes it easy. I want everything that's greater than -8. So that's going to be to the space over here. I put a parentheses at -8 because I don't have an equal to. And then I can just read this interval from left to right in order to write my interval notation. So that's from -8 to infinity. That's all done. I did not care about anything that's happening outside of the logarithm. I just take what's inside of that logarithm and I set it greater than 0. In this example over here, there's stuff outside the logarithm. Do not care. Do not care what's outside of there. All I care about is inside that logarithm. Inside that logarithm needs to be greater than 0. That's all I care about in order to determine what the domain is for this function. So then it's just a matter of quick solving it. So that's just an add 5 to both sides, no problem. And then make it easy to write that interval. I make a number line, draw a 5. I want greater than 5, so that's going to be going to the right. I put a parentheses at 5 because there is no equal to there. And then I just read this interval from left to right. So I start here at 5 with a parentheses, and I go towards positive infinity with a parentheses as well. In this example, I have a mixture of all of the different things, and all of those different things can contribute together in order to represent the overall domain of this function, because this mess is still a function. I've got all three, so I've got a denominator, I've got a logarithm, and I've got a square root. That denominator, I want to set equal to 0. The logarithm, I want to make sure that's less than 0, and that square root needs to be greater than or equal to 0. I said less than, but that should be a greater than. So I just set them all up separately. The square root greater than or equal to 0, the denominator equal to 0, and the logarithm, it's both, needs to be not 0 and not negative. And then we just need to solve each one of these one by one. So solving this one, I would subtract the 10x and then divide by 3. So x needs to be greater than or equal to -10/3. Over here in the middle, I would add that 4 to both sides, and then I would square root as a solving step. Whenever I square root as a solving step, I get 2, but then I need to put a plus or minus on there. So I know x cannot be positive or -2. And then finally, I come over here and do a quick solve. I subtract that 8, and then in order to get rid of the negative that's on the x, I divide both sides by a negative. But by dividing both sides by a negative, that turns the inequality the other direction. Now that's a lot. And so now what I want to do is trying to write that interval without a graph. That's crazy talk. So instead, I'm just going to put these all on the same number line in order to be able to determine what my domain is. So on my number line, I just put those numbers. And then one by one, I want to try to like talk about like what is going on. So x cannot be positive or -2. So around positive or -2, I know I'm going to have gaps. So I need to hop over these numbers. Then over here, x needs to be greater than or equal to -10/3. So right here, I want to bracket and I want to go to the right because that's where the bigger numbers are. Now this arrow is going to kind of keep going, but it needs to still skip over this spot right here because x also can't be -2. So we want to be bigger than -10/3, but we still don't want that -2. Same thing with the 2, so it would keep going. And it's not going to get past here, though, because x has to be less than 8. So this is going to be kind of the end because we want to be to the left of that 8. So we want to be in between that -10/3 and that 8. And we want to skip over -2 and 2. So now we write this as an interval reading from left to right. So we start right here at -10/3. We skip over -2. We skip over 2, and then we stop at 8. So here's our bracket, -10/3. We skip over -2. We skip over 2, and then we stop at 8. That would be the domain for this function. When looking at the domain of a graph, we want to think about where are there x values with no graphable outputs. So in this area over here, we do have graphable outputs because we can see that there's definitely graph there. Right here, we do have graph because up above, we've got a cat. Um, Up above, we've got a point. So we do have graph there that if we put something in for -2, we get some good output. So this domain kind of like toodles along and all of these values are good. We talked before about how we definitely have a good output right here, even though we don't have outputs above and below. So all of these values here, -1, totally fine. -3, we definitely have a point, so we're okay. However, once we hit -4, there's a problem there because that open circle means we approach that value, but we don't quite reach it. So there is a gap at -4 that we can't quite reach. We could continue along here at -5. We definitely have a good graph. And we continue along the way into infinity. So we reach positive and negative infinity, but we need to skip over -4. So that is why our domain is -infinity to 4, and then -4 to infinity. Whoops. We can do the same thing over here. These aren't quite functions. They don't quite have domains, but we can think about that same sort of thing. Right here at 4, we definitely have graph. We have too much graph. So our domain kind of like toodles along here. And because that arrow keeps going, we reach positive infinity. But over here at 2 and 1 and 0, there is no graph. I don't see any graph above or below me. There's no output values at 2 or 1 or -1. The lowest we can go is right here at 3. And we would have a bracket there because there's a filled in circle underneath that thing. So that makes our domain 3 to infinity. When we look at this one, we can definitely reach -infinity because we've got this arrow that kind of keeps going. -1, there's definitely graph down there. We're okay. At 0, there's graph down there. We're okay. So we kind of like tootle along. I keep seeing graph below me. So I'm putting those input values and I'm getting all of these output values as good. Right here, there was our double up point. So we kind of keep going, keep going, keep going. There's always graph. I look up at 4, there's graph there. 5, there's graph there. If I went all the way up to 800, there would be graph up above. So that makes the domain of this function -infinity to infinity. That is it for our video on domain restrictions. Remember, if you see a denominator, it cannot be 0. If you see a square root, it should be greater than or equal to 0. And if you see a logarithm, that should be greater than 0. If there's none of those three, then it's going to be all real numbers for your domain. A function, you should put one thing in and get exactly one thing out. Domain is your input, range is your output. And remember, that's all alphabetical. Thank you for watching and have a good day. Bye.